Good morning, guys. Today is April 27th. We're going to go over a few things about mixtures and solutions. You've actually had all of this material before. You had it at the beginning of I guess it was this year, right? Beginning of the year. But I wanted to go over it again because it is important for you to understand mixtures, suspensions, colloids, and those kinds of things. But again, you've had all of this, so this should be kind of more of a review, and I am going to get everything set up. All right, so when we have a mixture, we can separate three parts. One is a solution, which is what we have been talking about, where it's a homogeneous mixture, all right, of two or more substances. So our salt water, our sweet tea, air, those are all solutions. It's weird to think a solution is a gas, but technically it is. And then under heterogeneous, we have suspensions and colloids, and a lot of times those guys can sort of look like a homogeneous mixture because they have sort of, best way to explain it is temporarily floating particles. So the first one I'm going to go over is a suspension, okay? And that is a heterogeneous mixture technically, okay? Now a suspension, when you shake it up, it looks like a homogeneous mixture, okay? But over time, they will settle out. So for instance, I know you've taken it before, it was a really nasty pink antibiotic you probably took when you were younger. It was a liquid. But if you ever noticed on the container, it would always say shake well before taking. And that's because it was a suspension. So when we shook it, the particles were temporarily suspended, okay? And if you leave it long enough, the particles will float to the bottom. But after you shake it, it looks like it's a homogeneous mixture. Now a colloid is the homogeneous mixture as well. Sorry, heterogeneous mixture as well. But those don't actually settle out of solutions. So even though we think of milk, milk's actually a great one. Milk is a colloid. If you ever notice on your milk container, it says homogenized, and that's because it's a heterogeneous mixture that they've kind of fooled into making it look like it's a solution. Which is why when you have your milk at home in the jug, it doesn't separate into the fat layer and the water layer like you would get if you milked a cow. Okay? So those are the three things we're going to be talking about. So you need to know that many colloids appear homogeneous because the individual particles, you can't see them. They're not large enough for you to see. Okay? And one of those is fog. So fog is actually a heterogeneous mixture, okay? There are particles, water particles, and colloids can do something kind of neat where the particles are a little bit large enough to scatter light. So that's why when you have your car headlight shining out, you can actually see the beam, and that's actually a sign that you've got a colloid. If you actually took mayonnaise, Jello, any of those things, and shined a light through it, you would actually see a light beam like a laser, okay? And that little light beam laser is called the Tyndall effect, okay? And light scattered by the colloidal particles, and so that's why we can see a light. Now, we did talk about this at the beginning of the year, so hopefully you sort of remember it. Now, here are some differences between the solution, colloid, and the suspension, okay? Solutions are homogeneous. Our particles are atoms, ions, and molecules. They do not separate, and you can't separate them with simple filtration, okay? They also don't scatter light. A colloid is heterogeneous, but it looks homogeneous. Your particles are pretty large molecules. It doesn't separate, and it also cannot be separated with filtration. However, you notice here it scatters light. So if you look like you have a solution that's homogeneous, if you took a light beam and you could see the actual light beam through the liquid, then you would know you had a colloid and not a solution. A suspension is heterogeneous. Particles are pretty large. Sometimes you can even see like little chunks suspended. It'll separate if you just leave it standing long enough, and it can be separated with filtration because its particles are large enough. And sometimes it scatters light, but it's not transparent. You can't really see it. So those are the three differences between those three types of solutions, okay? All right, so let's go through here. So we're going to do color coordination, okay? So I'm going to use yellow here. So yellow is going to be our solution, okay? Green is going to be our colloid, and maybe I love purple. Purple will be our suspension. Okay, so we're going to go through each of these and decide, is it a solution, is it a colloid, is it a suspension? All right, let's start with this first one on the left. There we go. All right, a mixture where particles are easily seen and separated by settling or filtration. So the only one, and I'm sorry my phone is stinging. Always happens, doesn't it? It can be separated. It's the only one that can be separated with filtration is a suspension. All right? A mixture containing a solvent and at least one solute that has the same properties throughout. So the one that you can't really tell, you can't really separate, okay? That would be a solution. All right, next one down. Oops. Okay, a mixture containing small undissolved particles that do not settle out. Well, that would be a colloid. All right, so let's look at these now. I'm going to go down in a minute. Milk. So we already talked about that, right? Milk is a colloid. Now Kool-Aid, you can't really separate those out by filtration. You can't really see the particles, right? So that would make it a solution. Syrup, same throughout, right? Okay, so that would be a solution. Ocean water. What would that be? Well, if I take ocean water and I put it in one of my little buckets, right, it eventually will settle out. And the only thing that settles out is a suspension. All right, vegetable soup. Okay, well, vegetable soups, that's nice and chunky. We can shake it, we can mix it up so it seems homogeneous, but it wouldn't be. So that would be suspension. Yogurt, all right? Yogurt seems homogeneous, but if we took a light, you would see that it is in fact a colloid. Do you notice that most of the milk products here are colloids? All right, chocolate milk. If I have chocolate milk and I leave it sitting long enough, what sinks to the bottom? The chocolate, right? So the only one that has stuff settle out is the suspension. Okay. Paint. I don't know how much painting you guys have done. But again, if you leave paint long enough, that's why if you go to the store with your parents and they put it in a little shaker, and it's because it does settle out. So that would be a suspension. Muddy water would as well, right? If you left it sitting out, the dirt would go to the bottom. So he's a suspension. Shaving cream. All right. Shaving cream is actually a colloid. Okay? That is a colloid. It's got large particles. Vinegar. I don't know if you guys know, vinegar is just water, a few other things, and acetic acid. So if I have water and an acid, that's going to be a solution. All right, Italian dressing. We definitely know that's heterogeneous, right? And we also know that after I shake it and leave it a little bit, the oil and water separate again. So when it separates, it's a suspension. Okay, butter. Again, milk products, where do they go? Colloid. Okay, smoke. So let's think about smoke. If it's smoky or somebody's burning leaves and you have a headlight, right, you would be able to see the beam of light from your car. So that is a colloid. Okay, gasoline. All right, when you get gasoline, you can't really separate it, right? Now, if you put it with water, it sits on top, but gasoline would be a solution. What about soda? If I left my soda sitting long enough, would the sugar or the carbon dioxide go to the bottom? Nope. So he is a solution. Honey. Honey doesn't separate either, right? I don't think it does. So he's a solution. And last but not least, I don't know if you realize this, but glass cleaner is pretty much just water and ammonia. And they don't separate, because I know I've had my glass cleaner sitting out here for a couple years. It hasn't. So there's examples. Let's look at this next one. All right, separating mixtures. I don't want to make this take too long, because I know you guys get a little bit antsy. All right, so we did this before, separating mixtures, and there's different techniques for separating mixtures. A mixture is two or more different substances that are not chemically combined, okay? So a mixture can be a solution, okay? A mixture can be homogeneous, or it could be heterogeneous, right? And under heterogeneous, we already talked about, we've got our suspensions, we've got our colloids, all that stuff, okay? They're not chemically combined, which means if they're not chemically combined, then I can separate them using physical methods, okay? In other words, no chemical reactions occur, okay? So you don't have to remember your chemical reaction stuff. Which separation technique depends on which physical properties they have. So for instance, filtering will work with a suspension, okay? But filtering's not gonna work with milk, right? All the milk's gonna come through. So here's some different ones and kind of figure out what to use. Sieving, okay? And that's kind of like if you've probably seen it where people would go dig for gold and they'd have these little pans and they'd have little holes in them and you would shake it and the smaller particles would fall through, but the larger ones would stay in the little sieve, okay? So that's great for like mixture of sand and gravel. So the gravel would stay here, right? But the sand would fall out because it's really small pieces. Filtration. I think everybody knows what filtration is, right? We have some filter paper. We have our funnel, right? We have our solid and liquid mixture. So, I mean, you could even have ocean water, right? Because ocean water's got salt, ocean water's got sand in it, it's got bigger particles. So basically your filter paper is, if you could look under a little microscope, it actually has little teeny tiny holes, okay? Kind of like fabric. So the smaller things are going to go through and the larger things are going to stay in there. So if you pass a mixture of sand and water through a piece of filter paper, the water molecules are small enough to go through, but the sand particles are too large, so they're not going to go through. Now, the liquid that goes through is called the filtrate. All right, the solid that gets stuck, we usually call a residue. Okay. Evaporation, I think everybody knows what that is, and probably the most common one is if I have salt water or sugar water, either one of those, okay? If I filter salt water or sugar water, it's all going to go through, okay? But what we can do is we could put salt water into a little bowl, heat it up, okay? And then what would happen to the water? The water would evaporate. And then what's left? You'd have all these little salt particles left in the bottom of the little bowl, okay? So evaporation is for separating a soluble solid from a liquid, okay? NaCl is soluble, sugar is soluble, both of those things are, but if I remove the water, then they go back and they're just solid salt or solid sugar, okay? All right. Distillation. So we talked about this before, if you do recall. And the big thing about distillation, it's for separating a liquid from a solid, or better yet, it's a liquid from a liquid. Okay? That's what it's really good for. Okay? Because, and so this isn't a great representation here, but I do like this little setup because that is what it looks like. But what we can actually do is we can put, say, methanol and water in here. Now, both of those guys have different boiling points. So we know water is 100 degrees C. I think methanol is around 40 degrees C. So if I put a little flame here, when this solution hits 40 degrees, the methanol is going to come off, but is the water? No, the water's going to stay in there. He doesn't boil till 100. He doesn't become a gas until 100. Whereas the methanol becomes a gas at 40 degrees. So distillation, which we're going to get down here, fractional distillation, that's where we separate a liquid from a liquid. And that's usually what distillation is for. Yes, you can take salt water and evaporate the water and be left with the solid in the bottom of the flask, which would be down here, right? You could do that, and then all the water comes off, okay? So what happens is the water evaporates, and then this little thing here, it's actually surrounded by, and I wish you guys were here because we have the equipment, I could show it to you. That little thing here is actually surrounded by cold water running through it. So as soon as that gas particle hits the sides of the cold glass, it recondenses and then it turns into water and goes into there. But the same thing happens if you're trying to separate one liquid from another liquid, okay? So if I kept this guy, say I kept it at 50 degrees, okay? All of my methanol would come off and collect into here, okay? And then what will be left here is the water, because it's not going to turn into a gas until it's 100 degrees, okay? A really good example of this, and I know you guys have, you may or may not have seen some of the reality shows on moonshine. Yes, we're going to talk about moonshine, okay? And this is what they do. That's what they do. They have a liquid, I think from corn or another grain, and it's got water and it's got alcohol, right? So they cook it at a certain temperature, the alcohol comes off, goes into the little beaker, which I think they probably use drums, and so then they get the alcohol here and the water stays over here, okay? And that's what we refer to as fractional distillation, all right? Then we have paper chromatography, which I'm pretty sure everybody did in bio, I think. I actually have a lab to do this, but of course we didn't get to it. But what happens is you have a little solvent down here, right? And it wets the paper, okay? And then this guy will move up the paper. And then what it does is it separates, say, the different colors in a pen. Or there's a lot of things that will do that you can only see under UV light. And that's really what we use it more in chemistry. And we actually have a blue light here that if we could have done it, I could have shown you how if you have a medication that's got, say, Tylenol and aspirin, can't spell it, if we put little dots of the medicine, you would see that, you know, the Tylenol might only go to here, but the aspirin would go up to here, and so we would be able to tell which is which. But probably the most common one you've seen is the paper chromatography. Okay, this just explains how we would do that. We're going to make a small spot or line of the mixtures placed on this little pencil line, because pencils do not bleed like ink, so we like to use pencils. Paper's lowered to beaker that has a little bit of solvent. And then as the solvent, aka water, moves up to the paper, so your solvent, right? Just like if you stick a paper towel in a little bit of water, the rest of the paper towel will absorb it and kind of moves up. Same thing. All right, as the solvent continues to go up the paper, the different colored inks spread apart. If the inks have high solubility, they're carried further up the paper. If they have low, they don't move as far. Which brings me to the whole idea, and I don't actually have notes for that, but I do want to write this up here, is dissolving. Okay? Now, why does something dissolve in something else, or why doesn't it? And it used this phrase, like dissolves like. Okay? And what that means is polar dissolves polar. And on the other hand, nonpolar dissolves nonpolar. Okay, so what the heck does that mean? Well, let's think about it. Who is the most famous polar guy that we've worked with this year? All right, water. We all know at this point water is polar, right? If we draw water, you recall this. We've got really electronegative electrons there, little positives here, and so I have two poles, polar. So water is polar. Anything that is polar is going to dissolve in water. Okay? Sugar. Sugar dissolves in water because sugar is polar. Okay? Remember it's C6H12O6. Look at all those oxygens, right? And then look at all those hydrogens. So he's got two different poles. Okay? Now, oil, on the other hand, oil is nonpolar. Okay? So what happens when I have oil and vinegar? Remember that vinegar is just what? Water plus acetic acid. Okay? They don't combine. So why is that? Because oil is nonpolar, vinegar water is polar. So you have to have nonpolar polar. Another example. All right? When you go to the gas station or your parents and it's raining, you'll see the gasoline, because everybody spills it, right? There's always a little bit. You'll see gasoline, you'll see like a sheen on the water. I think sheen is that, but I don't know. On top of the water. Why is that? Well, gas is nonpolar. Water is polar. They don't mix. Gasoline and water won't mix. Okay? So you need to remember the phrase, all the way back up, like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Okay? All right, let's go through this little worksheet here. We're only going to do little sections here. All right, separation technique and who it matches with. Sieving. So which one of these descriptions is sieving? What does it separate? Separates larger solids from smaller solids, right? Let's see, I wonder if I can draw a little. There we go. Okay. Filtration. Now that's when we have a liquid and a solid, right? Separates a soluble solid. Nope, A doesn't work. An insoluble solid. So this would be D. Evaporation. That's when we have a soluble solid, like our salt water or sugar water. So that would be A. Okay? Distillation. Now this is distillation, not fractional. This is regular distillation. And that is going to separate mixtures of liquids with different solubilities. Yes. E. Am I missing something? Separates a liquid from a soluble solid in solution. Sorry. Okay, or did I flip-flop that? They're almost the same. B and A are almost the same thing. We'll just get that. Fractional distillation. Remember, that separates liquid to liquid with different boiling points. So that is F. And chromatography is where we separate mixtures of liquids with different solubilities. So if something's polar or nonpolar, it'll follow that liquid as it moves up. If it's a polar liquid, the object that's polar is going to follow it. If it's nonpolar, it'll stay at the bottom. So that is E. All right. So let's look at this. Which separation technique? If I want to separate red dye from a bunch of inks, that's chromatography. If I want to separate sand from sand and water, what do you think? Filtration. Separating oil from a mixture of oil, water, and ethanol. Okay, that one's a little harder. So I personally, because they all have different boiling points, but they also have different solubilities. So if we go look at our different techniques, distillation would work. And actually, chromatography might work as well. Okay. Separating pebbles from a mixture of soil and pebbles. Well, that's sieving. Okay. Separating water from salt and water. We could use distillation. We could also use evaporation, right? Separating salt from a solution of salt water. Same thing. Distillation or evaporation. And separating stones from a mixture of dirt and stones. That would be sieving. And I might have spelled sieving wrong, but you guys know how well I can spell. All right, so I hope that helped. What we're looking for on Wednesday, I'll go ahead and give you a heads up. Wednesday, we're going to sort of do like a little like formative assessment. We're going to take all these things we learned about solutions, and we're going to see how well you can do on them. Okay? All right, I'll talk to you guys later. Bye.